All right, so you've probably been seeing me playing around all week with my my wonderful white Transit Connect out there. It is not Jack's. I actually purchased this one. I bought it back in May. It was non-functional. It now has about 8,000 miles on it that I've actually put on it, so I'm close to 10. So I've driven it quite a bit, and I have a great time doing it. I've done 2 road trips on it. Now granted, they were 250-mile road trips, round trip. It took about 4 days. I never stopped charging when I wasn't driving.
But it's a road trip.
Yeah, that's a road trip, I know, yeah. So there's a beautiful picture of her right by the charging station inside the garage by my house. If you notice right back here, here's the bed to my 94 Ranger that I'm converting. It's been sitting there for about 7 years. I have two other EVs that I'm working on, the 94, and there's actually a 98 Ranger EV in the garage as well. It's one of the factory Ford ones. It actually drove on the trailer when I bought it, and it's one of about 6 red ones in existence-ish. There's no real number on it, but it's really relatively low in the red count. So there's like 200 remaining Ranger EVs, and that's one of a handful. So that's a little background on me. So why did I decide to replace the heater in the Transit Connect? Well, it was purchased for $6,500 from a dealer about 2 hours away from my house, non-running. He had no clue why it wasn't working at all. He told me the battery was bad. He told me I could replace a cell or two. It was a 72-volt battery pack. He told me that the charge point station that he had taken it to, the charge point guys dialed in via satellite to it, and they said that the battery was bad. I said, oh, okay, that's interesting. I don't know anything about electric cars. It's so what are you going to do about it? No, I don't have an EVSE or any of that stuff, so I'll have to get all that. I did. So that's why I have the vehicle, why it wasn't running. It was not starting, so long story short, did I change anything? No. The vehicle itself wasn't doing anything when I bought it. And I basically I needed to get the diagnostic software, so I downloaded that. I found a laptop with Windows XP Service Pack 3 on it. I got a capacitor leaf light, I made a cable, I got it all figured out. It took about 3 or 4 days to get all that ordered. In the meantime, Mr. Cochane in the back here decided that I needed to check my what do you call them, interlocks? The battery disconnect interlock things. It has 2 independent battery packs underneath the car that are put in parallel, two 14 kilowatt hour packs. Sure enough, both of those were wide open, so as soon as I closed those, I got some contactor clicking that I wasn't getting before. However, it wasn't closing the main contactors, it was just pre-charging and not doing anything beyond that. So I decided that I needed to see why it wasn't pre-charging. I disconnected a half pack underneath from the car entirely, and it actually pre-charged and closed its main contactors, not hooked into the bus of the car. So it's funny that one half pack doesn't care what the other half pack is doing at all. It just turns on. And the other side was getting to 260 volts, whereas this one was 350 when it would close. So what I was seeing, I have some oscilloscope traces, but basically it was flatlining when it would reach the current limit that was being allowed through the pre-charge resistor. And I'm like, well, something is on all the time. And the next night I went underneath there with the Ambition. Now granted, you got to remember it's May in Michigan, so the summer's coming, and I really don't need a heater. So I'm like, you know, the best, what's that?
The perfect time to fix it.
Exactly. Well, so I didn't, of course, but I'm like, well, the best thing it could be is the heater's bad. So what do I check last? The heater. So I started pulling main fuses out. I pulled out the Bruce charger fuse. That wasn't it. Well, that's a good thing. I pulled out the air conditioner fuse. That would be bad. It's going to be 100 degrees tomorrow. I'd like that to work. Then I pull out the heater fuse. Turn the key, hear the full contactor click, everything starts up. I'm like, awesome, I got a fully electric car that drives now. I just got to plug it in and charge it. It had been sitting for 1.5 years and had rolled 1 mile on the odometer. I got the service history from Ford when it went in, and they actually said, if I had checked this earlier, it would have been easier. They said that it had aftermarket equipment added, we cannot service it. Well, aftermarket equipment, I'm assuming, was the Azure Dynamics powertrain that Ford actually sold. So that's kind of the backstory. So I have a bad heater, and I ended up removing it and just leaving the pre-charge fuse out. Coolant heater was bad. So why was my coolant heater bad? Well, that is full of goo. That has been sitting open. I actually have it in the van right now for 4 months, and it hasn't dried out one bit. It's just a gelatinous mess. Coolant actually comes in here. I'm hypothesizing here. It flows to the back side. It goes through here, flows back up through and out on the other side. So there's an inlet and an outlet. And on the one side, about half of the passage was blocked, and on the other side, it's almost entirely blocked. So I'm not exactly sure if it overheated first or it gooed. The type of coolant they were using was it's a Ford coolant, but it's an organic acid compound. It's like Dexcool. And I'm guessing someone put non-Dexcool style coolant in there, and it may have done this, or it may have overheated and caused there's a whole lot of things that could have happened here, but that won't happen again. I'll show why in a second. This is actually inside on the electronics board. There's a nice chunk of corrosion growing here. There was actually coolant in this area. Over here, this is all conformal coated too, which is surprising. But right in here, there was another crusty growth starting. If you look at it, there's actually kind of a brown goo, and I was thinking that was corrosion too, but that's actually, I believe, the acrylic conformal coat that they had put on the board. So the solution to the corrosion was the Evans waterless coolant. I decided to go with just to try it. I figured if I have no water in there, it can't boil, it can't, I really don't need to cool anything. This actually has lower cooling properties than water. It'll transfer less heat. It's a mixture of ethylene glycol and propylene glycol and some inhibitors. It's like 60 or 70% ethylene glycol, 20% propylene, and some other stuff. So this was about a 3-hour process to purge out the original stuff. I ran a coolant system cleaner through it. I ran hot water through it. Then I ran a Evans prep fluid through it, which is a hydroscopic fluid which absorbs water. And then I decided to put this in after I had plumbed in everything. Like I said, the prep instructions said to warm your engine up. Okay, how do you warm your engine up when you don't have one, let alone nothing in the loop? So I just used the hot water heater. I have a hose going to the outside to wash cars with, and I turned up the water heater and I filled it up with hot water, all half gallon that I could. And you know, I didn't get a whole lot of nastiness out, but I assume it's working good now. It took a fair bit of time to bleed the system and purge it and get all the air out. I drove it around with the coolant pump on for a couple of days to get the air out, and every once in a while I'd get a big slug of air out, and I'd go fill it back up with some more coolant. So there's about a half gallon in the little loop that is the heater system on the Transit. So this is actually Jack's, but I had an idea. I'm going to take a Chevy Volt heater that I have sitting in my basement and put it into my Transit Connect, because I can't seem to find a Transit Connect heater, and you know, it can't be that hard to do. It's about the same power output level. About a third the size. It's quite a small unit. This one's like this big, and the old one was huge. Same voltage, so I needed a test bed for the Volt heater because Jack had one and no one had built one into anything yet. Well, I'd find it a fun project. I don't know who else would in my immediate vicinity, except maybe everybody in here. And a challenge to myself, being an electrical engineer and all-around hobbyist and getting everything done kind of exactly how I like it, is I wanted to keep it as factory as possible. So if I don't have to drill any holes, I won't. If I can do everything with connectors without cutting off cables, I won't. So it involves a lot of research on the back end to find connectors that mate and work with everything. So I'm going to go through basically the few steps of putting it in. This is the only one I don't have pictures for because it was already mounted and it's hard to see. So I maintained the original mounting holes of the original heater. There's 4 screw holes in the top, but I had to actually change it to a 90-degree mount. So I used 2 pieces of angle aluminum, about 1.5 inch aluminum, 6 inches long. Drilled some holes in it and mounted it. All the fasteners are stainless steel, 5/16, 12, 20. Is that right? Fastener thread size? What? 5/16, 18. Yep. So yeah, all that's there, and it's all hex fasteners, and it's all pretty nice stuff. Plumbing, it didn't go in the exact same spot as the other one. It went close, but I had to make some new tubing. So the Eberspacher heater out of the Volt has 3/4 output and inlet, and the Transit has 5/8. So I had to transition to 5/8 in a fairly short area. So I actually came out 3/4 on both ends, had 3/4 inch 90s, went to 5/8 in a small adapter that Dorman actually makes, and then went up. Tried to minimize the 90s because everyone is a flow reduction, but you have to have them in some places. Like right here, I actually used one big piece of 5/8 tubing in a U shape instead of having 2 sharp 90s. It's actually probably one of the best things I could have done. Everything is double hose clamped. I don't like leaks. Leave it at that. Hose clamps are cheap. Here was a bit of a fun one. The ECU that I wanted to use to control it via the control scheme was fed to an input and an outlet temperature or thermistor value. And I didn't know the state of the original thermistors that were in it, and I figured I could just buy some new ones. So I took and measured it, and the way an NTC thermistor works is at 25 degrees C, it has a resistance value. So in this case, at 25 degrees C, aka 70-ish Fahrenheit, it's 50 k ohms. And as the temperature goes up, the resistance goes down. So what I did is I took a thermistor, taped it to a piece of aluminum tubing in an oven, an industrial style oven, put a thermocouple right next to it, put some Kapton tape around it, so the aluminum acts as a thermal mass so that there's not a large fluctuation in the data I'm getting. And I ramped the oven up in 5 degrees C increments. So I got data to look something like this. It took about 6 hours on a Sunday afternoon. I was bored, I guess. So you can see here's the temperature in degrees C. Here's the actual degrees C reading on the thermal device I was using. Here's the thermistor value in thousands of ohms. And here's the Vichet 50K thermistor that I'm actually using now. And then there's a 1,000 ohm difference over here in a stabilization time. So you can see as I go up in temperature, the worst it's off is 3,000 ohms, and the best it's off at the top end is 0.7. And if you look at it, basically, if I was to use the Vichet one without any compensation, I would overshoot temperature from what the factory had. So what I did, Mark actually set it up for me, but we took a 820 ohm resistor and put it in series with the NTC, and it actually now feeds a slightly inverted signal back into the ECU so that it's not going to overshoot, it'll undershoot, but I'd rather have it undershoot than overheat. So this is probably a little bit of overkill, but yeah, it was kind of cool to do. So earlier this week, you probably saw us for about a day and a half huddled around one of Jack's test benches trying to get the actual heater software to work again. Me, Colin, and Mark were kind of banging our heads against a wall there. So some of the things we actually ran into was we had a ground wire not connected because we were trying to do the Mark's original board hooked up to the Eberspacher, but we had not hooked up the single wire CAN ground. So once we remembered that in about an hour, we had some timing issues, and we had a bad heater, which is actually pictured here. And it took a while, but we ended up figuring it out and got it up and running on the bench again. And then we had the EVTV Dewey, the 2. Actually, we found out had it's not really crosstalk, but it's a noise from the differential transceiver. So basically, we had to remove that to get the single wire CAN chip to work. So basically, I drove around all night last night with heat that was solid on, but it actually worked. Right here is one of the examples of a custom high voltage harness that I made to interface to the heater. So this connector here is the original Mitsubishi heater that was in the Transit. It has its interlock for high voltage, so the car will turn on. This is actually the bulkhead connector that goes through the heater so it stays waterproof. Right here I have 2 ring terminals, and right here is the Delphi connector. That's a $50 connector that then interfaces back to the GM heater, or the German heater. So I basically made a custom harness so nothing had to be cut or modified. Just small attention to detail right there, kind of looks good. We made a custom thermistor harness to the ECU. So thanks to Mark, we got the original. Brian, who made that connector?
I didn't make the connector, I gave you one.
Who's the manufacturer?
Sumitomo.
Sumitomo. So I actually had to ask Brian a connector question, and it was one of the brands I'd never heard of before. I looked at Odoo and like 5 other Japanese connectors because it's a Japanese heater. I looked at Molex and everybody, and nothing had a pitch this size, and it was just kind of weird. I actually have some connectors on order, but they won't be here for a week and a half because they're shipping from Japan. But right here, there's 3 lines in this that actually hook to the NTC, and under here is this is the inlet coolant to the heater, so the inlet temperature sensor's under here under this Gorilla Tape. I'll put some proper foil tape on here in the future. And under here, you can barely see it, actually here you can, is the outlet temp. It's a little further away than I wanted to, but it was the nearest metal that I could get on because rubber tubing doesn't conduct so well. I needed to get CAN from the vehicle, CAN bus for the heater messages. So fairly close by to the heater is the DMOC 645, which is CAN controlled. There's only one CAN bus in the entire vehicle. So what I ended up doing is making a pigtail harness that kind of plugs into the original DMOC amp seal 23, plugs into the DMOC up here. I pull off CAN high, CAN low, and 12 volts to run my my conversion board. So basically what we tried first was using the modified CAN Dewey to see if we could actually get the heat to work, and that's what I drove around with all night last night. This uses there's a single wire transceiver on there with a load resistor and some other jumper wires to actually make it work. Mark made that for Jack. That's what worked in the first time. So I ended up with heat that was uncontrolled at about, 4 o'clock like yesterday. However, it was pulling 9 amps continuous from my high voltage pack. It was getting 115, 120 degree air blowing into the cabin is what someone had measured, I believe. So pretty nice air. It's nice to have heat this time of year. Here's the single wire harness going down to the heater. I picked up a couple power lines from the battery for testing purposes. So this is actually mounted when we go and look at it after this, if you'd like, right to the front of my DMOC for now. It's not weatherproof at all. It needs to end up in a case or a compartment. If it was to rain, I would probably remove it. But basically what we have is the EVTV Dewey 2, the Teodora CAN Dewey 2, I'm sorry. We've actually removed the chip here that was causing the communication issue. Right here's a single wire CAN chip. We have a load resistor here, single wire CAN output to the heater, CAN high and CAN low input from the car, and power and ground. And as of half an hour ago, we have heat that is controlled via the vehicle now. So what I'm actually doing, this is a picture of the Transit's diagnostic software, but the original heater was controlled via 4 analog lines. So there was 4 MOSFETs inside the heater that would be pulled low to turn on the heaters whenever it called for a heat zone to turn on. So I could have fed that into a CAN or EVTV Dewey, and then put out single wire CAN and done it via analog. However, the vehicle's diagnostic software actually has 4 heat messages for diagnostic purposes, not for actually controlling the heater. But I know they're here, so they're on the CAN bus. When I turn it on, it turns them on. When I turn it off, it turns them off. So why can't I read these in my conversion board, basically set a power level, and then feed it back into the heater? So it's kind of a, incoming variable gets set, output message. And you can see here, these were actually reading negative 15F and negative 25F without any thermistors on there, and those started working yesterday. These are the inlet and output temperatures of the cabin heater. So yeah, it started working. So one of the big parts was actually finding the CAN messages that actually outputted. However, it is diagnostic, so it ended up being in the 600 range for the message ID because it's not really anything critical. It's just, hey, I need to know for diagnostic purposes. But we actually were able to find a DVC file that I thought had nothing in it, which actually told us exactly what messages were the heater messages in the diagnostics area. So we'd spent maybe an hour looking, and we had found something that seemed promising when we turned the heat on and compare it to no heat on, but nothing was really easy to find. But here, this is out of SavvyCAN. What we have is a time base down here, and I actually don't know what this is, but it's just on or off basically, isn't it? So the 3 signals we're looking at, 3 are on off. So cab heat 1, cab heat 3, and cab heat 4 are either on or off. They're just digital bytes. Cab heat 2 is actually a PWM signal. And then you're also looking at the pump signal right here. So at a point in time when I turned the heat on, pump went on, cab heat 1 turned on for, let's say, 5 seconds. It didn't detect that it was getting hot enough, so it turned on cab heat 2, which is actually this purple line. Don't be thrown off by the scale here. It's just, it went to 100% PWM, so basically on. Here, cab heat 3 turned on, and here cab heat 4 turned on. So basically it called for full heat. And then when I turned it off, right here, that's why it dropped, it turned off 4, 3, 2, 1, and then turned the pump off. Obviously you want to keep the pump on until all the heating zones are off as long as possible. We repeated that twice, and that is actually real data. So I'm almost done, but Mr. Collin over here was asking me, hey, why are you replacing the heater in the Transit? I said, well, it's broken and whatnot. And he said, oh, okay. Did you ever try finding one? I said, yeah, I looked on eBay for about 2 or 3 hours, and the only 2 that I found were like $1,600 or something like that. And I felt that was too much money for me, and I felt like just having another side project. Well, he said, oh, that's interesting. I said, oh, why is that interesting? He said, oh, here's what's funny. Colin lives an hour away from me in Grand Rapids. He said, well, I have 3 of them. I'm like, oh, okay, great. So technically I could, and I may still go get a Mitsubishi heater again and put it in. But that's one of the
$4,800.
Well, he told me he's not going to use them ever, so I'll take them off his hands. Yeah. So yeah, that's pretty much it.
$15.99.
Yeah, exactly. It does work. It turns on and off. We had a little bit of a software thing around noon that we were trying to figure out. No clue why it's working now, but it just works. So that's a good thing. And
how many kW is the
have any questions?
heater?
Yeah, so the whole heater is technically 6.6 kW. For some reason in the Transit, it goes up to 20 amps input from the 360 volt pack. I haven't done the math, but I'd assume that's somewhere close to full power. And then starts to throttle itself back to around 9. And it'll hold 9 the whole time. I don't know, that was just a funny quote I found from Einstein. But Yeah, so it stays around 9, so I assume that's about a little less than half, so 2.53. Yep.
300.
Back voltage.
320 to 380. 360 when it was doing that.
20 amps at 260 is 7.2 kW.
Oh, maybe it's overshooting. I don't know. It doesn't stay at 20 for very long. But what's funny is I'm running 5/8 tubing through my heater, so I have more flow than Jack does. Maybe lower pressure, but more flow. He's running 3/8 tubing with a Purebird pump, and I'm running some, it looks like a little PC coolant pump thing, but I actually get less power output than he does, so, which is surprising because I have more flow. I don't know if orientation of the heater has anything to do with it. It shouldn't, but.
No. How are you saying you have less power output?
So he has a higher voltage pack
On
than
the
mine,
electrical side.
and I also have lower current. So he was reading something like 11, 12 amps, and I was only getting 9. So I'm sending the exact same full power. Yeah.
Yes.
He might have more heat transfer.
Well,
I have more heat transfer?
Heat
I have
transfer
more.
is all about the flow. It doesn't matter what. the
Yeah, but
pressure
if I
is.
have more
That's
heat
flow.
transfer, I should have higher current levels,
But
not lower.
the heat transfer is the delta, so when the cold water, so to
Okay.
speak, comes in across that first element, is
Yep.
your maximum transfer.
Okay,
At the other end, you have a minimum.
okay,
If you have higher flow, you'll end up transferring more heat across the same energy on the heat side.
okay.
You should have higher current.
I should have higher current then, and I actually have lower current.
Assuming the efficiency is the same all the way across, in both comparisons.
It just seemed a little odd to me. It's only a 1 or 2 amp discrepancy. However, my system does heat up faster too, because I have a lot smaller loop and I have a lot better flow. And it's 1.5 gallons, and Jack has, 2 chargers hooked up at Delphi DC to DC.
How much
power
power
is
is
this?
in the loop?
His pump or my pump?
His pump.
His pump's a Purebird,
But
but
you said there's like 2 amps difference.
I'm talking high voltage power, not
Oh,
versus
sorry.
12 volt.
Purebird pulls 12 volts.
Yeah, yeah. But, yeah, I'm glad to have heat. I'm thankful to everybody that helped me out this week. And
Can I ask you, are these vehicles something that somebody who doesn't, write code and figure this out, could they drive it
Yeah.
pretty reliably?
I don't write code.
Which vehicle?
Yeah, okay. The heat
The
transit.
Transit Connect is a great vehicle. You don't have to know anything about software.
Yeah.
When Jack, they tend to seem to have some breakdown issues, and you kind of need to know how to repair them occasionally. But since I bought mine, I've had no breakdown issues at all. Nothing has gone wrong with it.
Probably if you use it all the time, it's gonna work better anyway.
Yeah, so my vehicle actually came from Detroit Edison, so DTE. They had only driven it 2,400 miles in 2 years, which is actually really low.
Yeah.
From what the dealer told me, now granted, we all know how shady he was, he basically said that it was used in events like the National North American Auto Show, Cobo Hall, stuff like where they had to drive vehicles inside and couldn't pollute. So they only use them hardly at all. There's a fair number of the vehicles out there. I know my university actually has 4 of them. They had more, I think. They're always parked, so I'm not sure if they actually work or not. I'm actually not going to drive mine in the winter because I'd like to keep my eager drive functional.
We have plenty of driving.
You're gonna swap them out for free?
For free.
Yeah. Well, you said you have plenty of them.
For free.
Oh.
One free lunch.
Yeah, so they're
That's
good.
not my favorite quote of Einstein. My favorite is when he was trying to explain the telephone. It's like a cat where the tail's in New York and the head's in Los Angeles, and you pull on the tail in New York and it yells in Los Angeles. Wireless is the same thing, but without the cat.
Cat's on the roof. Which way did it? Yeah, yeah. Well, good. That was everything. So if you want to go take a look, it works, and I have fairly good heat.
I got a question.
Yeah.
Is the heating element the what, positive temperature coefficient, or
The
is there
heating
a-
element is PTC. So basically, I don't have to even really worry about it overheating. I do, but it actually shuts itself down. So when I'm commanding full power out of it, I get it dropping back. So as it gets up to around the 180 degree F range, I was dropping from 9 amps down to 6 amps. And I wasn't dropping off my commands.
Okay.
So it was basically throttling back. And
Okay.
as soon as the transit actually starts turning off its heat zones, it started working again, but or turns them back on after it cools off a little bit.
Yeah.
One of the disappointments with the Eberspacher is it's rated for like, what, 6,000 watts
6.6 or so.
at 0 degrees centigrade
Inlet temperature.
inlet temperature.
Yep.
wow.
I don't know how you're going to keep it cold.
So I want the water to be about 170 Fahrenheit. Well, up there, it only puts out about 1,500 watts or 2,000.
Yeah. I wonder if I have better flow, maybe it would help, but I mean, I'm pumping, I don't know how many gallons per minute through there, but it's a 5/8 line through something like a computer pump, so it's not pits. Get it?
Yep.
The image I've always had is the cold water coming in and the hot water going out and dropping across, kind of like an electronic circuit. And these heating systems don't work that way. Maybe they do, but what I measure is the same temperature all over the place.
I was dropping about 1 degree.
And so the heat exchanger is the key. If you want more heat, you get a bigger heat exchanger. If you want more cooling, you get a bigger heat exchanger. Running the flow up faster doesn't help. More water doesn't help.
You have to pull the heat out of the water.
Yeah, yep. And since I didn't touch any of the heater core or anything like that, it's...
Air or surface?
Yeah.
Well, we're kind of at the end of the day. What time is it?
2:30.
2:30?
Jack, we haven't talked about a little car, or a little bike.
A little, oh, okay. We're going to have, and that's what I was going to open it up to. There's always a few people that have got something going, a little something they brought to show and tell. Nabil Henke, and I'm sorry, what's your name? Is
Ray.
Ray Scheifler.
Ray Scheifler. Actually, one of the things they're supposed to talk about anyway, and they may have forgotten this, we've been on again, off again, just about a little device that does one thing, measures temperature and reports it can. Kind of like my limb cab that measures current, reports it can. I'm trying to work on a GPS that does GPS and reports it can. And I look around for these things on the internet. I've got a great big machine with like 64 gigabyte of memory and 30 terabytes of drive and a 60 meg link to the internet, but I can't find any of this stuff using Google. One of my fond dreams is we make some of these little modules, put them up on the website, and other people are looking for that too, and suddenly I'm selling a Brazilian of them. That little limb cab current source is made by Lim, Haas, yeah, Lim. Their electronics division makes it, but it's classified as an automotive part. So none of the electronics distributors will carry that device. And the automotive guys don't know what it is. And we're the only source on the internet for this device. And every time I order, they have to look around and, oh yeah, we do have that. This is the lost product of Lim. It's lost in limbo. And we actually sell a lot of those things, but not to you guys. Mostly to Germans and Swedish and that sort of thing. They come in all the time buying that little, because it's a simple device. You run a cable through it, and you can query it for the current over CAN. And so that's one of the things Nabil and Ray have been working on for several years. The problem is they keep becoming distracted with robotics projects. And here they have created a mini bike that runs on a car alternator.
Yep.
And he did drive it down to the house last night, so it actually worked. And that comes out of their work with some high school kids and some robotics programs. But I do hope they mention my hand temp. It's just a little thing to where I can get a temperature over can. And then any of you that have other stuff, we'll kind of talk about that too. Is John Felker here this afternoon? He said he was going to drop by. He was kind of interested in what we're doing and sent me a brand new set of glasses. I don't know how he knows how much this would appeal to my sense of whimsy, but if you'll remember my Commander Cody safety glasses, this is me all over. And they'll probably put those in the store. I think his pricing is $50. But as I get older, that all gets less fun.
Are they readers or are they?
They're readers
Okay.
with LED lights inside.
Gotcha.
And batteries. Comes with 4 batteries in a nice little case, and the batteries supposed to last 50 hours. So they work for me, more so now that we're doing circuit boards and so forth. And so Ray Schaefer and Nabil Henke and the can-do battery tip sense.
Yep. So the can-do name, Jack and I went back and forth about because I'd come up with this notion of a product line of can-based accessories that would be simple to use for the EV enthusiasts who didn't want to know how to mess with getting and setting bits on the CAN bus. But he'll say, all right, take this, you plug it in, you push that button, and it works. And so the can-do temp came about when I had an unfortunate run-in with getting burned by the cold. So having a daily driver and living in Iowa, I had a particularly cold time and had a poorly constructed temperature protection method. So I just got a little temperature switch, stuck it in my battery box and said, well, I hope that's good enough. And it was a pre-configured temperature. I couldn't alter it. I couldn't, I did throw it in the refrigerator, but okay, it worked, but I didn't know at the time how precisely it was hitting that temperature or not. So I had that enabling or disabling my charger, and then I put in a little space heater. My battery box was sitting inside of the cabin of the car, so I figured, okay, space heater's going. It'll nice and slowly warm up the whole thing, so I should be all right. Following that charge, I had dramatically reduced power. I've not made the time to pull one of the cells out and actually measure the lost capacity from that cold charge, but I know there was damage done. And so I leaned on Ray. I'm like, all right, look, we got to do something. And so having some EVCON chargers, we started developing the can-do temp around that.
What kind of reduction in range did you see?
I never actually ran it dry after that. I've always been conservative, assuming I'd get about a 10 to 15 loss %. Yeah, here's the can-do module. And it's based on an microchip pick. Yep. So no, I've not precisely measured it. That is on my to-do list. After I die riding a little tiny motorcycle.
Where's the gun?
So,
Where's the gun?
where's the, yeah. So we wanted to have something that had more than one measuring point because thinking it through, if I've got a single battery pack, I could probably get away with a single point, maybe, maybe not. It depends on how controlled the environment around that box is. If I've got multiple battery boxes, I don't want to have a million analog thermocouple lines going all over the place inside of an EV in a noisy environment. So we wanted to have reduced complexity in the wiring, as well as eliminating false positives. So we didn't want to, if this is supposed to protect a multi-$1,000 device, we don't want to have it say, okay, it's good when it's not. And obviously inhibiting charging when it's too cold. We want to know if it has all of its sensors or doesn't have all of its sensors. And we wanted to make this with an explicit purpose of measuring temperatures and regulating the charger. Not doing everything under the sun, not being a development kit in a box, but having just a fixed purpose. Like killing a fly. But bottom line, it needs to save my pack.
He's a sailor now.
So, again, two functions. Read multiple temperature points and regulate the charger. So, we developed it to have 7 probes per module. That relates to the number of bytes in our message on the CAN bus. We said, all right, we're going to do an 8-byte packet. 1 is going to be a sanity check overall, and the other 7 bytes are going to be temperature values. And we based it around the one-wire temperature sensor, because looking at a variety of things, that was going to be really simple to work with, relatively robust. We can get the probes already connected onto a wire. It's small. You can tuck it in between cells.
They're isolated.
They're isolated.
They are metal cased.
I have plastic casings now.
Oh, they're plastic. Then you can get them in metal casing or plastic casing. That metal casing is actually isolated.
Yep. And if there is noise that is going to interfere between the module and the probe, it's going to interrupt the actual signal, not give you a false signal. It'll actually go, oh, it's not there anymore. It's gone. And we have a pair of Chenic chargers, so that's what we worked with. Just some EVCON CAN bus. And we found documentation that was helpful. But we wanted to be able to configure it very simply, so we chose to go ahead and use a Bluetooth serial board as a reference point. And so we have pinouts, so you just plug a little Bluetooth to serial adapter into it. It gets powered by the CAN module, and then you just crack open a terminal program on your laptop, and you can talk to it, configure it, read messages off of it, etc. And we wanted it to be discrete. So one could say, well, it's already connected to the CAN bus. Can't you just connect it anywhere to the CAN bus? Well, the thing is, you can have multiple battery boxes in your car. And so this device is supposed to be 1 per battery box. So if you have multiples in the car, in your battery box, in a sealed condition, how do you, if you just plug them all in right now and start talking to one of them, how are you absolutely sure that that's the one you're meaning to be configuring and not accidentally configuring a different one? So I said, all right, forget that. We're going to program it discretely over a separate medium, and that is the serial. And we have a
Bluetooth serial. What are we talking about?
Bluetooth serial.
Yep.
I also designed some USB serials with the same pin out because I wanted some with the same pin out. So.
Yeah. But then being inside of a battery box, you don't want to have a whole lot of loose little tools you're fumbling with. So the idea of having the screw terminals, I love screw terminals for a lot of applications, but we didn't want to have someone slip with their screwdriver and have it fall across terminals. It's like, all right, let's try to get this toolless, and that's why it's got the latching connector, despite Jack's preference otherwise. Which I'm not knocking, it's just, you know. So it does latch in, and we haven't noticed any issues with them disconnecting. Go on.
And if they were to disconnect, because they're digital sensors, it wouldn't handshake, we wouldn't hear from it, we'd freak out and inhibit charging, is the safest condition. I'd much rather end up with an uncharged car in the morning than damage the pack because it was too cold.
Yep. And so you can have multiple, like I said, up to 7 probes in one box. So you can put them around the periphery and also in the center, so that way if you're worried about extreme cold, you can, you know, from the environment, you can do that. Or if you're worried about if I have too much insulation, I want to make sure that I'm not getting too much thermal concentration in the middle. You can put probes all over the place, wherever you want. But bottom line, for the purpose we designed it, is are any of these too cold? And so that there's not a problem having too many of them in that situation. And the other part that it does is it listens for the EVCON. Other chargers behave differently, but the way the EVCON works that we've used, you plug it in and the EVCON starts announcing to the CAN bus, hey, I'm here and this is the battery voltage I've seen. That is all. It waits for a charger controller to tell it to do something. And that's why Jack's little box is so handy. And we're like, well, we've already got a CAN bus. We can already program this chip. So why do we need that and that and that? So we just put that feature directly into the CAN-do temps, but also to be able to make that distinction of, is it too cold? So that's that. One other bad thing. Yeah.
Where does the can connect? I saw 8 little
There's
Yep.
7 3-pin connectors and 1 4-pin connector.
Oh, okay.
The 1 4-pin connector is 12 volt ground, can high-low.
Yep. So you just plug that right in
Did
there.
we put a termination resistor on bould?
Yes.
Yeah, there's a little jumper.
Yeah,
that
there's
does
a jumper
termination.
for termination.
Yep. So I should have.
Oh, they've got a little box there made, which is 3D printed. Yeah. So they could
The second one here. The other one's going around
goes on the
the
canvas.
Do you have them with you such that we can buy them?
Huh?
Can we buy some?
Yes.
How much do they cost?
$120 for a kit with 4 probes,
It's not.
and probes are 10 apiece additionally. Where's that serial?
The USB serial?
Yeah.
You would have.
Yep, here it is. Okay, so
Do you have a jumper on that for powering?
yes, this is one I was using.
Okay.
All right, so let me illustrate the simplicity of plugging it in and powering it up. Now, I'm not going to plug in power over the serial because I don't have a serial device, or I'm sorry,
We don't have 12 volt handy.
But-
it can be back powered through the.
it will be
serial
powered
port.
through the USB for demonstration purposes. So I just line up my 5 volt onto my serial, and I'm going to plug in over USB.
And then naturally, like all demonstrations, it's
It
going to
lights
fail
up.
horribly. Oh wait.
It will end horribly. No.
I don't understand Bluetooth. It's just a USB port.
So, the China makes these wonderful Bluetooth serial bridges that are 4 pins. Your board supplies it 5 volts and ground, and there's a TX and an RX. I said, that's a nice pinout. I've already got a header for it. So I asked China to make me some USB to serials with the exact same pinout. So for demonstration purposes, it's easier for us to power it via that 4-pin header. I can pull out one with Bluetooth modules, and you can see the Bluetooth module, which would be more useful in a car. For this, it's more useful to just be plugged in.
Because you're wired into the 12 bus.
Yeah, in the car, you'd be powering in via the 12 volt bus. For this demonstration, when you're sitting on the bench, it's handy to power it from your laptop. With laziness and convenience.
So hopefully you can read that. This program doesn't have a lot of features, including font size. So if I go ahead and hit the help screen, I've got a nice little list of things to do, including continually display all programs. So if I do Control P or Shift P, oh come on now. Oh, it's not powered. It decided to disconnect itself.
That's one of the disadvantages of having it on a longer header like that. It'll tilt. So,
Oh, this?
yeah.
Yeah.
Well, that's why the
You
Bluetooth
don't
handy enough
need the serial connected. It's just
Yeah.
for
just for
setup.
configuration.
You may want to read. Yeah.
It was working. There it goes.
There we go. Alright, so I've got no devices hooked up. It's all zeros. So I will plug this in to any of the ports, doesn't matter. and I'm actually going to push button 1 on here for 2 seconds. It'll flash, and you can see on the screen it popped up and said no probe found. Why did you find no probe? It didn't stick with it. There we go. There we are. So now it's hot. So it has 1 probe found. I can go ahead and plug in another one and hopefully have it latch in.
Does it have to be sequential, or can you plug into like 1 and 6?
You can plug into any of them.
Yep, plug into any of
It's a one-wire commute.
Yeah, it's
Technical details, it's a one-wire
Maxim's
communication bus.
one-wire stuff.
So you can plug into any of them. We do remember which serial numbers are plugged in, and so if you swap out a probe, you have to resync it. Otherwise, it'll say, "Hey, I lost my probe."
Yep. Light stream of local temperatures. Lowercase d. There we go. So now it is going to display for me the temperatures of these probes. And if one of them gets disconnected, it will show up with an error. I can plug it into any of the ports again, it doesn't matter. And it'll come back, you'll see it.
What temperature does it think ice is?
I knew you were going to bring that up.
I know, actually.
15, I'm guessing it's 0,
12, 9,
1 or 2.
8, 6,
You may have to start as
5,
well.
4, 4,
It's not a bad,
3.
So there's there is thermal mass involved in this sensor.
Yeah.
And
you put some salt in the cup,
One.
check it
We're in at 1.
Yeah, you can
Fire a couple hundred rounds into it.
Yeah, hitting at 1 and a glass.
Let's take it out in the car.
oh, by the way, they're waterproof.
Yep. That's actually one of the advantages of the steel-cased ones is it's stainless steel. So I haven't tried it yet, but I want to. Put this into a crimp ring T fitting onto a liquid line to get liquid temperatures. So if you want to put various probes throughout your warming or cooling loop.
They have little bulkheads you can do that too, so you can thread it in and then tighten a little gland nut down.
Sure. Yep.
So these sensors are not the fastest to respond, but for the purposes of is my battery too cold, when your probes are strapped to the battery and have been for the last 5 hours,
Yep.
doesn't matter a whole lot.
And so plugging multiples in, do I have the right cable and power set?
No.
I'm not sure that I do. So if I go ahead, if I were to do capital D, of course there's nothing to show, it will see all of these nodes on the CAN bus. And so how do you know which node is which? Well, I can go ahead and type in A for address, and then I can put in 1 through 255. And now this is in decimal. So we can just, within our own can-do ecosystem, you can just say, all right, I've got temperature module 0, 1, 2, 3, 4, and 5, and 2 is the front left battery pack, 1 is the one right in front of the firewall, and 3 is the pack in the back. And so when you're listening with CAN bus, the messages will come in, and you can see which one's which in that mode.
And if you're really curious about that, I do have them in my car, and we can actually pull up the CAN stream. I don't have the exact same firmware that you've got on there, so I don't have all the fancy serial menu, but I've got a Bluetooth CAN bridge, and so we can see CAN stream from my car. It's a really boring CAN stream because the only thing on there are CAN streams.
Yeah. Oh, actually, I should put this back. So go ahead and set it as a charge master controller. I say capital M, and so now this Candy module is not only taking a constant measure of the temperatures that are still plugged into it, but it is also listening for a charger to announce itself on the bus. And I can go ahead and set a charge voltage of say 156 and a charge current of 4.
Don't put them in the capitals.
How did you do that? What's he typing?
Capital V and the capital V and the voltage you want for the charge termination. Yeah, termination voltage, capital A, and the current that you want to be charging. Both of those are 10 times the actual value you want because
Intensive of volt.
it's intensive
Tenths of an
volt,
amp.
tenths of an amp.
VC, you're charging to 15.6 volts and 0.3.
Yeah.
Yep.
The profile
Now, do you enter it normally, or do you have to enter it at 10 times?
10 times.
10 times.
So if you want to charge to 156 volts,
It's
you do
one-
capital V 1560
Now we're 156 volts, it'll charge up to.
Why didn't you do the math for us?
because parsing strings is a pain in the ass.
Yes, it is.
So you'd rather
We
they
do a very simple charge protocol. We tell the EVCON to go 1 volt higher than the number that you typed in, and when it gets to the number that you had typed in, we tell it to stop. So,
You don't have to do that, they'll come taper charge to that voltage anyway.
it will, but the profile that I want to be doing with my car is run constant current until I hit my termination voltage and kill it. I don't want any CC phase. So,
And another item you see here for the charger settings is external module count. Whichever one you designate as the charger controller, you can tell it how many other modules are on the network, the bus actually, to look out for. So if any one of them has lost a probe, it will tell all of them that, hey, I'm missing a probe. And if the charge controller sees any of them missing a probe, or it itself is missing a probe, if it became disconnected, cable got cut, or if you had a faulty piece, at 2 levels, it'll know that and it'll inhibit charge. So you're not going to get a false
Always
positive.
250K.
yeah, this is hard coded at 250K baud because that's what the EVCON is.
I understand.
Yep. Could be changed. It's software.
How could it be changed?
Well,
not-
we could change we could put different firmware on this to run at a different baud rate.
But it's
But-
not configurable, but.
Not
No.
configurable.
Nope.
Okay.
Again, with the purpose that this was built for.
And what's the CAN bus address, or can you configure
So, we'll get to the messaging structure.
that? All right.
So, unlike the Teslas, this is going to get into some pretty more structure of identifiers. So, unlike the Tesla and unlike most of the cars that are running in the standard identifier space, the EVCON is running in the extended space. And because I happen to work for a company that happens to use J1939, I'm very familiar with how J1939 is structured. And so we're using a similar structure to J1939. They run, J1939 is 250K baud, and you run with the extended mode. And you divvy up your message like so. The priority bits, the lower the number of the identifier, the higher priority it is on the bus. So they've shoved in the very topmost bits the priority space. And so you can say 0 through 7 of your priority. So if your message really has to get through, you can change that. The reserved and the DP, you fix at 0 because reasons of the standard. Then you've got your PF and your PS, which the PF and the PS specify either that it's a broadcast and what broadcast message it is, or that it's a destination specific with a destination message. And then there's finally the source address field. So all of our probes are sending messages that have a hard-coded priority, hard-coded PF/PS that are broadcast messages. I forget exactly what we're using.
1234.
That's okay. That needs to be changed because that's not technically a valid broadcast. But
Yeah, it is. It's in the spectrum.
oh, it's in the broadcast.
It's in
Okay,
there.
yeah. So we're doing a broadcast, and then you can tell which node it is by the source address. That's the 0 to 255 limit. So we changed the identifier field to figure out which one it is. When we're talking to the EVCON, this actually came from the EVCON spec sheet. EVCON is expecting messages from a F4. Actually, it doesn't care what the source address is for the BMS.
It tells you what it wants it to be.
No, it broadcasts. It tells you what it is. It will be sending out messages as broadcast messages of here is the current voltage and current and my statusy bits, and then you have to send a destination specific message to it. And I believe it doesn't care what your source address is, but you have to have the destination address correct, otherwise it doesn't listen.
So, by fact of wanting to have it as the secondary function of controlling the charger, we went ahead and said, all right, look, we're going to stick with the extended identifier, and it actually works out really good to have an extended identifier in an environment where you're going to have multiple devices of the same type. Let's all have them with the same base specific address, because that defines the form, how you should interpret that packet. Because one of the things that has been talked about this week is digging through and sniffing out what does this bit mean, what does that bit mean. And by using the extended identifier, you can go ahead and say, all right, look, this is...
when you're doing your filtering, you filter on these to figure out what the heck does it mean, and then this tells you where it came from.
Which particular device it's from. Yep.
Yes.
You're talking about just the identifier in that whole stream, not any kind of data path.
Yes, this is the 29-bit identifier.
Right. So you could put, if you were looking at just an identifier out of can, you'd see all 29 bits, just like you would with an 11-bit identifier. But this is just another way of actually divvying up or encoding what an identifier.
Yeah. This is some rhyme and reason to what the bits in the identifier mean.
Yeah.
And this happens to be a standard that is used by large over-the-road trucks, primarily diesels, as well as large boats via the NEMA 2000 spec, and via tractors via the ISO 11783 spec. So there's quite a few devices out there that speak like this.
Yeah.
Is it in locomotives, Brian?
Yes.
Yep.
Yeah, J1939, I believe, formally is for large diesel engines. And then Ag added their own specific messages on top of it, and boats added their own specific, which ironically, the GPS messages come from the boats. NEMA 2000 finds GPS messages, so there's this weird interconnection of the three standards.
All right. Yeah. So for everyone who's been having all the CAN info fly over their heads all week, bottom line is this right now is configured with a couple of simple lines in a terminal program through a serial connector to control a charger to 156 volts at, I think I said, 3.5 amps, and it has 2 temperature probes plugged into it, and it's preset to not turn on if the battery is measured at 0 or below. So without having to get into programming and whatnot, it's configured. And you can set a different, you can set an arbitrary minimum temperature. That if you want to say, all right, look, I want to be really conservative, don't charge if it's below 5 C. Okay, whatever, you can set that. So that is the CAN-Do temperature sense module. It is available on bolt-on-ev.com, as well as once I give Jack some inventory, he will have some as well.
Can I just get the temperature from it?
Yeah.
It's spitting the temperatures out via on the CAN bus.
Okay.
And that message.
Yep. And is that address configurable?
The source address portion of it is configurable.
Okay. And so is it always extended?
Yes.
Okay. And is this 7 bytes, and how are they encoded?
We have a full technical write-up on that.
Yep.
So
yeah.
we do. We can provide you a Savvy Can description file if you'd like.
A DVC
A
file,
DVC
yeah.
file.
Absolutely.
And so but
It's an integer offset by 40 for the 7.
40, okay.
Yeah. 255 means I don't have or I'm not expecting to have a probe there. 254 means hope I've lost a probe there. Okay. Also following the J1939 spec, you always send an 8-byte message, and if you don't know what to do with the bits, you set them to 1. If you read the standards, when they say reserve bit, you always transmit that as 1, because then in the future, when you do want to use that, you say all 1s in this chunk means I don't know. So that's how you can handle differently versioned processors and things.
But I can change the source address
Yes. Yep.
through configuration or
Through serial.
Yep, through configuration.
Yeah, through serial configuration.
Yep. So that's the Sense module. And we intend to develop more can-do product line, such as a heater control module. So that way you have these temperature sensors in your packs, and outside of your pack you have the logic to be able to control the heater power. So that way, you got temperatures floating around the CAN bus. Different devices on the CAN bus can do different things with that information. So one can control a charger, one can control a heater, one can display on your dash, because the information is there and available.
You mentioned like a charger enable or heater control input output. How does that work?
That's not on this board.
This
That would be
is
a different board
Yep.
that would consume these temperature messages.
Oh, okay.
yeah.
Well, sorry, this one does control an EVCON charger.
Right, right.
Oh,
But
well-
I just meant do you have a charger enabled, disabled? That's what it sounded like in the first.
Well, this one does have charger enabled disable because it talks to the charger directly.
Right. Okay.
Because it acts as 2 separate nodes on the CAN bus.
I think it's a cool product.
Yeah.
So Lightning?
Yeah, so this is something that we did most of the development on last year, and since then we've been distracted with other things such as Lightning.
This horrible, horrible little vehicle.
Lift it up really high so the people in the back can see.
Yeah, it's a little bit heavy.
Throw it on the turntable.
Yeah, I was thinking about doing that. So, another expertly executed horrible idea.
Yep, I will. So, as you may have recalled last year, we had a horrible 3-wheeled device. That was named Banshee. This is a picture of me racing it in Detroit at the Detroit Maker Faire and having an insane time because stupid little vehicle on a track. And then I mentor, and Nabil used to mentor, a high school robotics team, and one of the students found the idea of a mini bike on the internet and said, hey, I should build one. We're like, okay, go for it. And then somebody at the makerspace says, hey, I've got these frames. And if you go to the next slide, we got these frames. And so that's how the frame came to us, and all of that tiny, tiny glory. If you go to the next slide, this is what I first showed people just the picture of the frame. Like, oh, okay, that's reasonable.
Mm-hmm.
Yeah, me for scale. They're like, oh God, you're doing what now?
Yeah. And just off of frame here is the second, or just out of the picture is the second frame. We decided to name them, the idea was we make one electric and one gas powered. So this is Lightning, the other one is Grease.
I would have said McQueen.
Huh?
I would have said McQueen.
Oh.
So the primary design criteria behind this thing is cheapness. This is a high school student doing it. His parents are actually footing most of the bill for it,
Yep.
but still cheapness. Also mini bike chassis. We wanted to primarily use COTS parts. We didn't want to have too much scavenged material on here just because if it breaks, it's hard to replace. Normally you think of cars in range. We decided not to think of range, but in runtime, aiming for about 30 minutes of runtime. Mainly, the purpose for this is going to be that he can take it to college with him and ride it to class and generally troll around the college campus. So it doesn't have to go.
Wear them on the feet.
What?
Get two of them, wear them on the feet.
Just about.
Yeah.
That'd be terrifying.
So it's mainly just because we can and for the wolves. When we respect,
Common off the shelf.
yeah. Battery
Nothing
pack.
crazy. And
Yeah, we don't want anything. We don't want a $2,000 motor that came from a company that has gone bankrupt, and we may or may not ever be able to get one again.
Oh, they didn't go bankrupt, they were bought by Bombardier.
Oh, okay.
They're the ones that win. Mission went bankrupt.
yeah, Mission.
Okay, sorry.
And this $2,000 motor would make that scream.
Well, I'm not doubting that. For our battery pack,
It'll make him scream.
for our battery pack, on Banshee we had used a 12S pack of Calbs, 40 amp hour Calbs. That was amazing, great power, great reliability, would not fit on this chassis. So life cells, particularly Calb life cells, were out of the question. They just physically would not fit. Banshee got 45 minutes of hard racing on 1.2 kilowatts. We said this thing isn't going to be hard racing, and we only need about 30 minutes of run time, and it weighs less than Banshee, and I don't know, let's just throw out a ballpark of 480 watts. Watt hours. So a 12S, 4P, these are Samsung?
Yep.
Samsung lithium ions. So, or lithium cobalt, yeah. There were 2.5 amp hours, 4 in parallel. So how do you deal with 18650 cells? You spot weld all the things. This is actually the arm of the high school student who was building this vehicle, and we routed out a jig, and were able to line up our 12S and built our horrible spot welder, and we're spot welding.
Tell us about your horrible spot welder.
Yeah.
So
this is a better picture of a horrible
This is the
spot welder.
larger of the two. The ridiculous idea was to just go to YouTube as source material, and there's videos of people taking microwave transformers and using them as spot welders. So we tried that. It was anemic. So I said, all right, crap. Hit the Makerspace message list and said, hey, look, we need a bigger transformer. So one of my coworkers offered this forklift transformer for charging forklift batteries. I'm like, okay, cool. In order to get the winding out, I had to actually completely disassemble all those laminations, and they were nice and gelled together. And so it was about 2 hours of peeling all those laminations apart. And it's running 4 gauge with like 5 wraps on the secondary on 120 volt mains, and open circuit is 4.5, 5 volts, and short circuit current on my 800 amp range on my clamp ammeter read 1100.
So some. This board is one of the other boards that I've designed. That's the Janky 1772. In this mode, all it's doing is turning on and off that little relay to turn on and off the coils. We're doing this entirely timing based, which is probably not the right way to do it, but that's what we're doing.
It worked.
And it worked. And it turns out that we need about 2 cycles of AC. The period of time that the relay is on is about 2 cycles of 60 hertz AC. So not very long to get our spot welds.
But they were good welds.
They're actually very good welds, and you can, if you go back, you can see the completed battery. You can see the completed battery pack that's been gloriously covered in lots of tape, and now it has even more tape on it. And we're really thinking about strapping a clock onto it, you know, because something entirely wrapped in
Take
tape.
it to school.
Oh yeah,
School, yeah.
Oh yeah, yeah.
Oh.
And get back to common off-the-shelf things. It's nice to be able to go to any Home Depot and find the parts for your EV. So the battery enclosure is it's 3 layers of tape about, and then we got some 4x4 PVC fence post, and just kind of trimmed that down and got a little clamshell, and then wrapped that in more tape. So it's a toy. It's not exactly high-end EV by any means.
So what kind of motor do we strap onto this beast?
Go to Napa. Got an
Well, no, that's too expensive. We went to the junkyard. We ended up using an alternator motor.
Which, by the way, the Ford alternators are a pain to remove the rectifier from. Use a GM alternator.
This one is a Subaru, or not Subaru.
No, it's
Suburban.
Suburban. Yep.
It starts with an S.
Yep. So we've got your stator that you'd recognize from an AC or a brushless DC motor. We've got slip rings right here with a pair of brushes right there that would normally go to the regulator, but we got rid of the regulator part, kept the brushes, got rid of the rectifier, just came straight out of the 3 stator phases to power with the brushless DC motor controller, and then replaced the pulley with a sprocket.
And we also are connected to the brushes and are running a constant DC field on the rotor to give us our permanent magnets.
Yeah.
Or
So
permanent magnets.
yeah, and yesterday we were having a heck of a time with how much voltage to apply to that to get a given magnetic flux. And
That's later.
okay.
That's later.
All right.
So some theory of how this whole thing is supposed to work. If we do apply current to the rotor, we end up with something that looks very much like a standard brushless DC motor. It's got your stator field on a brushless DC in-runner. You've got a stator field and you've got magnets on the inside. We also found, interestingly, that because we've got a sensored controller, we can run basically an inductive AC mode by just leaving the rotor open or shorted.
Yeah, shorter
Both
is always a
ways.
little bit better.
Both ways work. Shorter works a little bit better. The Kelly controller that we happen to be using needs to have sensors. We couldn't find any sensorless controllers in this size. There's a very unique and fun happenstance in that the rotor of an alternator is very commonly 12 poles, and the magnet cap on a CD-ROM drive brushless DC motor is also 12 poles. So we totally just stole the magnets from a CD-ROM drive and have connected that to our shaft to be the surrogate magnets for our motor controller. Some science. We actually tested this motor or alternator to see what we could actually get out of it. We found that this is a fairly well engineered in terms of one component doesn't vastly exceed the others. The field saturates at 12 volts, which conveniently, if you're putting it on a 12 volt car,
The rotor field.
the rotor field saturates at 12 volts, 4.5 amps. Meaning when we put more voltage and current through it, we did not see appreciable gains in our torque. So we said, okay, we'll run a maximum of 12 volts on it. The stator happens to melt when we go past about 200 amps, given the gauge of the wire, which also happens to be when the stator iron saturates as well, so happy coincidence. And we measured with so much precision of a torque wrench that at rotor lock, with just powering one field of the stator, or one phase of the stator, and with the full field current, we get about 18 foot-pounds of torque, which is a fair amount of torque.
That's stalled. That's not
Stalled, not spinning. We also found that the stator has about 40 milliohms of resistance, which if you're ever trying to measure the resistance of such a small resistor, what you have to end up doing is you get out a constant current power supply and a voltmeter. So ran 10 amps through the stator, grabbed the multimeter, measured the voltage, and then divided by 10 because of Ohm's law. On the next slide, I've got some numbers and some stuff, but before we get there, some abstract high-level motor theory. First, we've got Ohm's law. Volts is current times resistance. We also fundamentally have the fact that motors act as generators because you've got spinning magnetic field. And also your motor controllers are just chopping your pack voltage down to a lower motor voltage. So if you were to sketch out approximately what's happening at steady state on one of the phases, you've got a voltage source which is stepped down from your battery pack, you've got a resistance of the stator winding, and you've got a voltage being in opposition to this voltage, and that's the back EMF of the motor. So keep this picture in mind when we go to the next slide, and we've got some numbers here. What we're really trying to figure out is, how much power can we pull out of this thing and at what speeds. And given the previous measurement of the resistance of the stator, if we want to drive 200 amps through the stator, the voltage output of the motor controller has to be 8 volts greater than the EMF, vehicle's IR, which means that given our 12S pack, which is 44 volts, we've got a maximum EMF budget of 36.4 volts. If we've got more EMF, if we've got more back EMF than that, we aren't going to have our 8 volts of differential, and therefore we're going to be pushing less current. So if we come down to this graph, we've measured back EMF by manually spinning the motor at a given armature current. And so with 1 amp of armature current, the drill that we had hooked up measured 2110 RPM. We've measured 9 volts of back EMF, and we can calculate that out. And we don't start hitting back EMF issues, decreasing our current until we hit about 6K RPM. At full speed, with no more current being able to be applied, which would mean we have no more torque, we're running about 7K RPM. If we increase our armature current, we come down here and we see that with 3 amps of armature current, our max current RPM is about 3K, so we've got a whole lot more torque. And so that means if we want to extract maximal power out of this thing, we want to kick the armature current as hard as we can, and once we get to about 3K RPM, we want to start backing off on the armature current so that we still have overhead to keep torque. If you go to the next slide, this slide. This is a power curve from a AC50, and in particular, if we're looking at the horsepower curve, you're building, because you are in current limit mode, which the pink line is your current, because you're current limited, your horsepower is building with RPM. Once you hit the point where you can't deliver the current anymore because your motor controller is giving her all she's got, it's maxed out its PWM, it's putting full pack voltage to it, it can't do any more, your horsepower keeps pulling back. Well, if we can fiddle with the field current, we in theory can keep this line flat for longer, because we like extracting as much power out of things as we can. If you go, this slide explains a little bit of what I was just saying. We could just set and forget the rotor current, say, it's a value, don't worry about it, it'll work. But that's not as much fun as trying to extract all of the power all of the time. We want a stronger field when we're taking off, because we want more stall torque, we want more go at the low end, and we want to keep going faster when we get to the high end. You want to talk about bootstrapping?
Yeah, so with all that clear as mud, in short, we're doing something that no one thinks can be done. We've seen it done in the past with alternators. No one has done it to the power scale that we're taking it, and this is just the beginning.
We're hoping we can, melt one of these down while extracting piles and piles of power out of it.
So given that it's a toy and it's likely to be packed away in a closet for many months on end, we want to avoid as much parasitic load as possible, especially an imbalanced parasitic load. So we're utilizing a bootstrapping method to where even if that battery's plugged in, there's absolutely no circuit to be pulling any, not even the sensor circuit, to be pulling any power out of that battery if we're not wanting to. If the relay is off, there's no pack load because all of the pack goes through the relay.
But it gets rather interesting when you start saying, well, wait, how do you turn on the relay? Because our relay happens to be a 12-volt coil, not a 44-volt coil. So we had to get rather interesting with shenanigans. And yeah, these are some hastily sketched together things. That would normally be 44.4 volts. That's the full pack voltage. We've got our main contactor here. We've got our motor controller over here, and we've got our DC to DC down here. So what happens is you push the button, which bypasses the relay. Using this pre-charge resistor, you start charging the caps of the motor controller. At the same time, you're inhibiting the DC to DC from turning on. Once this capacitor gets charged enough, you open that switch, which enables the DC to DC, which then turns on the relay, which then gives full pack voltage into the motor controller and the relay. Because this wonderful pile of circular logic is actually rather interesting and allows us to pre-charge and allows us to not have a parasitic load.
Yeah. What makes it really crazy is that this switch is activated by a button that activates 2 other switches at the exact same time. So we have 3 switches that are acting, they're all isolated completely, but they're being activated and deactivated in parallel. So he mentioned the inhibit on our DC to DC. That inhibit is being activated when we have this pressed down, and then as soon as we let off, that inhibit is turned off, and then this turns on to do its thing.
So we're abusing the capacitors and the motor controller because we wanted to avoid abusing the capacitors and the motor controller. We do allow them to pre-charge up to the full voltage, and then we're just, stealing a little bit of their charge to get the relay kicked on.
How do you turn it off?
You turn it off with the other switch. That switch down there is just a toggle switch. Breaks the relay. Relay's open. There's no load when the relay's open.
Yeah.
I have a somewhat similar concept in the Miata, which makes it great for winterizing because, yeah, I should turn off my service disconnect switch, but I don't actually have to. If I weren't to turn off the service disconnect switch, I wouldn't actually be draining my pack at all.
Nope. Not even a JLD, not even voltmeters touching his battery if his car's off.
So some issues. We did not show up with this thing running today.
Or together.
What?
Or together.
Or together.
Yeah.
It's fine. So we had some very interesting issues. We found that if we have full field current on our rotor, that oversaturates the Hall effect sensors on the back side of it, which are using the tiny CD-ROM drive magnets. So we had to trim down our DC to DC. Accidentally toasted one of them because we hooked the resistor up wrong and trimmed up instead of down.
Their diagram with an illustration of the module was drawn backwards of the actual module. So when I'm sitting there looking at things, I'm like, okay, I put that pin right. All right. Yeah.
Yeah. Nope. That wasn't enough. So we borrowed a power resistor from Jack, and so now we've got a power resistor in series with our rotor winding to, drop a little bit more voltage and reduce the current a bit. That works fine now. We also found that in our initial bootstrapping that by turning on the motor controller, by turning the motor controller on at the same time that we were trying to bootstrap through the relay, that the motor controller was sucking too much power and sagging the voltage too much, which wouldn't give enough voltage for our DC to DC to turn on. So that's where the third switch in the set of switches actuated by that button comes into play, so that we don't turn the motor controller on until the relay turns on. And then we had it working on the bench, and when we transposed it to on the car, we reverse powered our Hall effect sensors and might have killed some of them. Might not have, because they actually, the Halls that we were using actually have a symmetric positive and negative power supply capability, so we might not have killed them. But now we've got 2 sets of Hall sensors on one ring and 1 set of Hall sensors on another ring.
Yep.
Finally, Nabil and I are both members of the Area 515 Makerspace in Des Moines, which is a bunch of crazy people who get together and make stupid little projects because we can. It gives you an opportunity to hang out with like-minded people who like to find problems and fix them. Area 515 is specific to Des Moines, but there are hackerspaces all across the world. So if you go to the Hackerspaces wiki and check out the list of hackerspaces, you will probably find one in your area. Oh, and by the way, if they have an open house, they probably, at least our space, really enjoys it when people come by with projects and cool things that they've done. And so anybody who has a car here, if you want to feel really popular, show up to an open house night at a makerspace. you will almost certainly have people coming out to check out your car, and they will have good, depending on the exact people that space is made up of, there's a high likelihood that they'll have good technical questions, and that they'll be interested. And if you've got problems that need solving, they probably will have at least ideas on how to solve them.
Yep. Yeah, and they'll also have facilities to do things. So the enclosure for the can-do temps, currently we're printing on the 3D printers at the space.
So, I was going to ask that.
Yep, and as are some of the parts for this thing. And actually, if you looked at the top surface of the can-do temperature module, you might have noticed the labeling. That was etched in with a laser cutter, because the 3D printer doesn't have resolution in order to print that small of text. I tried and tried and tried. So when you're wanting to do a special little thing but really can't justify the extra $1,000 to buy the tool to do the thing just the one time on your EV, there's a chance that the makerspace might have a solution for you.
They might have the tool, or they might have a very ingenious workaround.
Yes, involving microwave transformers.
Possibly. Hackerspaces.org. Specifically, you're looking for the list of hackerspaces. But yeah, they are actually a worldwide thing. Generally are made up of interesting people doing interesting things.
Yep. So, further questions on the stupid idea expertly executed? The bike.
Is it running?
Yes.
Yeah.
How fast is it going?
Fast enough to be scary.
Fast enough that
It doesn't have brakes yet.
Yeah, fast enough that we don't want to go any faster because it doesn't have brakes.
It's kind of chuggy right now. So the current the
thing-
Kelly controller has configurability. We haven't touched any of the configurability. We took it from China out of the box, put it on, plugged it in, and said go. We haven't actually tuned one bit of it.
So also interestingly, because we're running our magnets separate from the rotor, we actually have to rotate our Hall effect sensors into the appropriate alignment with the magnets so that the motor controller actually goes the direction we want and doesn't fight itself horribly.
Yep.
And currently it's doing a little bit of the latter.
Can I get the number on that motor controller? Can I get the number on?
That's KEB 1408.
Kelly Controls, it's their standard brushless DC.
They've actually got quite a variety on their website.
Kelly?
Yeah.
Yeah, Go to Kelly Controls, look at their brushless it was just the generic brushless DC motor controller.
Yeah. Yep.
This specifically is the 200 amp peak.
The first Speedster that Jack did was using a Kelly controller. So they do pretend to have controllers big enough for EVs, like cars, barely, almost. They got quite a selection for motorcycle scale stuff, and go-karts and
I'm
whatnot.
looking for one in the 2 to 3 horsepower range.
There you go. That's a
what
3
this
kilowatt.
is. 48 volt, 200 amp peak, I think.
Oh, the 48 volt's a problem.
How low do you want to go, or how high do you want to? They got them up to 90
I want
volts.
to go pack voltage.
I know they've got 96 volt ones, which would be good up to 120.
You have to look at what they got.
You'd have to look.
Yeah, that's why I was, actually doing work on a 400 volt input to a 2 to 3 horsepower or 3 kilowatt
That's
output.
some low current.
Really low current, but there's a reason.
Yeah.
So how much do you estimate these off-the-shelf parts have
On
cost
the-
you?
On this bike, we've got probably $600 worth of components that have been purchased for it. We did scavenge the DC to DC, and we did scavenge the main funky relay.
Well, the DC to DC was an eBay find from several years ago on another project I did that also had 2 wheels. The big relay is off of the forklift, and the big switch I got from work as well. That's an industrial. It's a knockoff of an Allen Bradley. It's okay. If you were to buy those new, pricey. But if you go through the yellow pages and look for forklift manufacturer repair shops, they might have used
Well,
relays.
We wouldn't have to use nearly this chunky of relay.
No.
We could use probably a $50 relay.
Yeah.
Definitely less than $1,000 worth of stuff on
Yeah.
the bike.
Yeah, so our ultimate goal with this is to develop it into a four-wheel vehicle, a go-kart, and our goal is to 0 to 60 in 2.4 seconds. That's already been hit by other teams that have a budget several orders of magnitude larger than what we're willing to put into this one. So this is actually not so much a challenge of engineering as much as it is also a challenge of economy. Because again, our goal is out of one of these alternators, 20 kilowatts peak. That yeah, that brushless motor right there is 40 kilowatts peak. 2,000, call it 50.
It was 35.
Yeah.
35 at the junkyard, plus a little bit of time to monkey with it.
Yeah, and if this really takes off as a functioning thing, there are companies that will make alternators, and a custom alternator will still be way less than $2,000. So we're just approaching a different angle on a problem, but really there wasn't a better option for a motor that would fit in that chassis at a sensible price point.
The speed limit of this item is contained within the Kelly then? The speed limit for the alternator motor is a function of how fast you can switch it.
How fast you can commute, yeah. I want to say that given our pull count, the Kelly should max us out at like 8K RPM.
Something like that.
Well,
8,000 motor RPM.
Your control loop's greatly simplified because you're using the Hall effects for your commutation.
Yep.
Yeah.
Yep.
It has a maximum frequency.
Yeah, it does have a maximum frequency, and we did look at it, and I believe it was like around 8K.
Yeah.
Is the maximum commutation. Well, it was something completely else, but when you factor in how many poles of rotor we've got, it comes to 8,000 motor RPM.
Yeah. Which I'm not sure that an alternator is really intended to go much faster than that, if even that fast.
Yeah, I mean, it's
So it's definitely something you want to ride on top
some
of.
ratio of the motor.
Yeah.
So the biggest cost was your control?
Batteries.
Batteries.
We've got about $300 of batteries. We've got 150, 170.
Yeah, under 200 for the motor controller.
Yeah, under 200 for the motor controller.
Yeah, purely a toy, but definitely an exercise in engineering.
A lot of principles involved.
Yeah, fortunately we've been able to give this high school student an experience that you would not get otherwise.
How do you kit out a vehicle?
How do you project it? Yeah.